So we'll start with the first couple of chapters that you guys have gone through, matrix transformations and Gaussian elimination.
Okay, this is on, right? Everyone can hear me? Awesome. So yeah, thank you. So we will be starting with matrix transformations and Gaussian elimination and talking a little bit about what it is. So remember that we can see any matrix as a linear operation applied to X. We can see it as a system of equations, right? This is how we've seen a matrix as. These matrices are used to do different operations. And so geometric operations we've seen are rotation, scaling, and reflecting. Okay? And remember, and we've also seen this in homework, the order of matrix multiplication matters. Okay? If I do it in one order, I could rotate by 30 degrees by the x-axis and then 60 degrees by the z-axis, but the order I multiply the matrices says which order I do those rotations by. So make sure to remember that. Okay, so what is Gaussian elimination? Right? We have a system of equations and we're trying to find the solution, right? So whenever we see a matrix, an augmented matrix, we can read out equations. So like we see over here in this example, we have these three different equations, these three different linear equations, and we can write it as a matrix, an augmented matrix. So the top row reads, it's 2, 4, 2, 8. We can read it as 2x plus 4y plus 2z equals 8. Okay? So we can build an augmented matrix, and then we can use Gaussian elimination to solve it. So how do we do Gaussian elimination? Remember that we have the different row operations that we can apply, right? We can multiply a row. We can multiply a row and add it to another, right? We can swap two rows. And so there's these different row operations that we can apply, and we apply it to the augmented matrix that we wrote our system of equations as, and we try to bring it down, we try to reduce it so that we can get to this basic reduced form. And what we want is we want to have a pivot in each row we can have a pivot in, right? And so a pivot for a row is when you have a non-zero value in a column and all values to the left of it. So all values over here are all 0. So in this matrix we've shown right here, we have a pivot in the first two columns, right? But the final one, we don't have a pivot. It's a row of zeros. Okay? And so that means, so we have those are pivots, and that's no pivot there. Okay? And so if we get to this form, then we can read across to get our solution. So the top row, remember, these are just equations once again, and so we can read it out as x plus 0y plus 0z is equal to -2. So that gives us that our we use x1, x2, x3 here, right? It tells us that x1 is -2. The next row we can also read, and we see x2 is -4. And then we cannot tell anything from the final row, so we don't know what x3 is. Okay, so in this first one, we have a pivot in all the rows. This means that we have an exact solution. We have a unique solution. In this second one we have here, we don't have a pivot in the final column, which means we have, and it's a row of zeros, we have a row of zeros equals 0, and so that means we have infinite solutions. But in the final matrix, we see that we have a row of zeros, but it's set to equal 1. And so that means we have no solutions, because 0 never equals 1. Okay, so do we have any questions before we move on Gaussian elimination and matrices in general? No questions? Yes? Yes, you can still have an exact solution, right? Think of it as you have more equations and variables. So if your final row is just a row of zeros, that means it's satisfied. Now, you won't have if you have 4 rows and only 3 variables, they're not all going to be independent, right? But you can still have a unique solution because you're only trying to find those 3 variables. Yes?
If in the exam you're asked to find solutions to a system of equations, by looking at it, you can do it directly. You still have to apply Gaussian
Travis, do you have an answer to that in the exam? Do you mind repeating that real quick?
So in the exam, they also like solve the system of equations and like by looking at it, like you can find like you can directly find the solution or by different methods. These will use Gaussian elimination or like
Show your work. So if it's basically like, don't say the answer is that by looking at the matrix, show you won't get any credit for that. If you see it through another way, just point out that way and like if it leads to a solution and good, we're going to accept it.
Yeah. So show your work, and the only exception to that is if it says explicitly solve it by Gaussian elimination, solve it by Gaussian elimination. Okay. Any other questions? No? Okay, then we'll move on to shortly cover what linear independence and span are. So, what is linear independence or linear dependence? Okay, a linearly dependent set of vectors means that we can write one vector as a linear combination of the rest. Another way we've also seen, a way of writing this, is that if we take a linear combination of all our vectors, we can get the zero vector without the coefficient for all this, for example, over here, a1, a2 to an, without all of them being zero. That means they are linearly dependent. Linearly independent means the only way when we take a linear combination of the vectors to get zero is that if all of these coefficients equals zero. Okay? So let's do a quick practice of this. We have these three vectors on the left. Are these linearly dependent? Right? So if we want to show that they're linearly dependent, then we need to be able to write one of the vectors as a linear combination of the other two. So it turns out that yes, we can. If we take -2 times the first vector plus 3 times the second vector, we will get the third vector, which means the third vector is redundant, right? We already got the information from the first two. Now, how do we figure out this -2 and 3, right? So what we can do is use what we learned previously. We can use Gaussian elimination. So we can write this out as an augmented matrix, right? We're trying to solve for what A1, A2, and A3 are. So we can augment it with a row of zeros because we want to make sure that the sum of these is equal to 0. And we try to solve. What are these A1, A2, A3? If we solve it, we'll figure out that we have A1 -2, A2 3, and then A3 is -1. Okay? So then you would see, oh, I have, not all of them are 0, I have an option, therefore it's linearly dependent. If you get that the only option is zeros, then you know that they are linearly independent. So that's what we see for this case on the right. They're independent. The only way that you can take a linear combination of these two vectors and get 0 is if you have A1 and A2 are both 0. Okay? And then span, that we said we would also cover. A span is just a linear combination of a set of vectors. So it's all the linear combinations of the set of vectors you're taking the span of, comprise the span of that set of vectors. Okay, so that's for this section. Are there any questions about that? Span or linear independence and linear dependence? Yes?
If there's more equations and variables, would that guarantee that one of them should be linearly dependent?
Equations, yes, right? And does that make logical sense? So what was asked is that if you have more equations than variables, can you be sure that they are linearly dependent? Okay? And the answer is yes. Yes.
So based on this, like, remember when I asked about
Mm-hmm.
you said there was going to be a unique solution and linearly dependent?
Mm-hmm.
How are those?
Great question. So the question was, for everyone to hear, if you previously, like when we're trying to solve a system of equations, right? If we have more equations than unknowns, can we still get a unique solution, right? If we've just said that if we have more equations than unknowns, then these equations are linearly dependent. The fact here is that 3 of those equations, if they are linearly independent, then we know there's a unique solution for them, right? And so even if the 4th one is dependent on the other 3, right, we still have those 3 that give us a unique solution. Does that make sense? Okay. Yes?
When we're doing Gaussian elimination, how much work do we show? Do we say, like, put a time interval 1 by 2 or by 3, or do we just write out the augmented matrices?
I believe you can just write out the augmented matrices, but remember, the more work that you show, the more we understand your understanding of the question. And also, it's a very good practice of just writing it down so that you know what is the row operation you are performing. Okay? Yes?
So when doing Gaussian elimination, do you need to normalize each row, or do you just perform any row operations to get to reduced form?
You're trying to get to reduced form, which means a pivot in each of the columns. I don't think that necessarily means you need to have a 1 in each of the columns. But once again, remember, it's easier to read off the solution if you do have a 1 in each column.
So I would
Yeah.
say whatever works best for you. In the case where you're trying to find solutions to a system of equations. But the reason we're asking from you to do this all the way through is that you calculate the inverse matrix right away with the same method when you're trying to find inversion.
Okay. Yes? Mm-hmm.
So if you get a solution, what does that mean? And like how do you know by doing Gaussian elimination whether it's linear?
In terms of what was shown in a couple slides ago? Over here? Great question. So how do you know that once you've done this, if it's linearly independent or linearly dependent? So when you're solving this in Gaussian elimination, right, you're solving for these A1, A2, A3, right? And if you have a solution for A1, A2, and A3 that does not have them being all zeros, right, then you know that you have a linear dependent, right? You may have multiple solutions for this A1, A2, A3 being non-zero if they are linearly dependent. But what you will find out is that if they're linearly independent, the only solution you will get is for all of them being 0. Is that okay? Okay. Great question. Any other questions? Yes.
So if you're given 4 linearly independent equations with 3 unknowns, that would be like an automatic no solution.
No.
4 linearly.
Okay, yeah. So you're saying you have 4 linearly, sorry, could you repeat that real quick? 4 equations?
Linearly independent equations for 3 unknowns.
So if you have 3 unknowns, right, would you be able to have 4 linearly independent equations?
No, right?
Yeah.
So it's automatic no solution.
Well, it's not that you have no solution. It's the fact that you won't have 4 linearly independent equations that are only in terms of 3 variables.
So imagine that you're
Yeah.
doing Gaussian elimination to solve that system, right? And you have 4 equations and 3 unknowns. So you have 4 rows and 3 columns. And you also have your augmented matrix. You have an extra column, right? You are guaranteed to have a row of zeros at the 4th row. And depending on whether or not the bottom right coefficient becomes 0 after you do the Gaussian elimination, you have either a unique or infinite solution or no solution. Okay?
So,
Can everyone see how this could be the case? If basically the system of extra equations is consistent, then you could have a solution there.
But then if it were consistent, wouldn't it be linearly dependent?
so if it's, oh, sorry.
It will always be linearly dependent, but you are talking about a case where you have more equations than unknowns, right? So if you have more equations than unknowns, you're guaranteed to have linear independence. Depending on whether the system is consistent with itself or not, you will get a row of zeros in the end, all the way through the augmented part, or no. If you don't, then it's no solution.
Okay. Is that clear for everyone? Okay, then with that, if you have any more questions, remember you can raise your hand and we'll come around and answer it. But for now, I'd like to pass it over for vector spaces.
Thanks, Annika. So basically we've seen so far that it's cool to use this matrix notation and representation. It allows us to very compactly write out systems of multiple equations. And we've also seen an algorithm to solve these equations, all right? Now we're going to take it a step further, and we're going to build up our understanding of linear algebra and introduce some concepts that are going to be useful in figuring out properties of those matrices and properties of those systems, especially when they represent dynamical systems that evolve with time. So to do that, we introduce vector spaces and subspaces, and also with those the concept of basis and dimension. Now, a vector space is formally defined as a set of vectors and a set of scalars, f, v and f respectively, that satisfy addition and vector addition and scalar multiplication properties. The properties can be found in Node 7 if you want to go and watch them offline, but they're essentially for vector addition, associativity. It doesn't matter if I have three elements, in which order I perform the addition, it will still give me the same result. Commutativity, u plus v equals v plus u. Then I have an element which, when I add to any element in the vector space, it will give me itself. So additive identity, the zero vector. And we have additive inverse. Any v has its minus v, and v minus v is equal to 0. So these seem all very trivial. Another very important property that you probably have seen is closure under vector addition. So for any two vectors u and v that belong in that space, u plus v also belongs in that space. And then we have scalar multiplication, which is associative. We have the element 1 in that set of scalars. So 1 times v equals v for all v in this vector space. And we have also the distributivity in vector addition and in scalar addition. So what is written out here as a times u plus v equals a times u plus a times v, and a plus beta times v equals a v plus beta v. So also we'll see that we have closure under scalar multiplication. So for any vector in v and scalar in R, a times v is also in that vector space. Those are like the formal definitions that might seem a little vague to most people, right? Now, usually we are interested in smaller spaces inside the general bigger space. Our bigger space is usually going to be Rn, an n-dimensional space that involves all of the real numbers. And to verify that a vector space V is a subspace of Rn, or any other vector space, we need to check 4 different things, right? We need to check that it is indeed a subset of Rn, or of the other vector space that we're checking. So every element that belongs in V also belongs in Rn. We need to check that if two vectors, v1 and v2, are in V, then their addition is also in V, so it's closed under addition. And we need to check that if v1 is in V and alpha is any scalar, then a times v1 is also in V. So it's closed under scalar multiplication. Finally, and most importantly, we need to check if it contains the zero vector. This is a very fundamental property. And basically, the reason that I pointed out these properties is that if I show that a certain subspace qualifies as a subspace, then it is itself a space. So it has all the properties that I showed in the first slide. And any linear combination of any two vectors in that subspace also belongs in that space, which is written out in this equation over here. So any v1, v2 in that subspace, any scalars a1, a2, a1, v1 plus a2, v2 is also part of that subspace, right? And also a note for jargon, for people who like it, we refer to Rn as the parent vector space of subspace, and V is a subspace of itself. Question? For vector spaces, we need you to prove all of the properties that are listed here, and you can find in Node 7. Okay, let me complete this section, and I'll open it for questions. So, as I said, 0 being in the vector space is really important. So, are these two subspaces of R2? The y equals 2x plus 2 line. Who votes yes? Raise your hand. Who votes no? Great. Why no? Does not contain 0, right? Is it closed under addition? Are you sure? So if I have x1, y1, x2, y2, and I add those two together, I get y1 plus y2 equals 2 times x1 plus x2 plus 4, not plus 2, right? So the new element x1 plus x2, y1 plus y2 is not in that vector space. How about the second guy? Yes, right? It satisfies all of the properties that we talked about. So that's essentially the answer. Now, wrapping it up, you saw what span is as a noun. So it's a concept. It's basically the set of vectors that can be written as a linear. So we define span, right, on a certain set of vectors. So span is itself a set, and it contains all of the vectors that can be created as a linear combination of the initial vectors in my set, right? So any vector that can be written as a1 v1 plus a2 v2 plus ... ak vk is in the span of v1 through vk. And spanning as a verb, as an adjective, means that I have a list of vectors that can create themselves other vectors that belong in a new vector space. So we say that a set of vectors v1 through vk spans a space if they can generate any element in that space. Now, the reason this is important is that we define bases as a set of vectors, right, that essentially are spanning a space and are all linearly independent. They have these two properties, right? So this essentially is the minimum set that you need to describe a space. That's what basis is. Basis is also a set of vectors which allows me to create any vector inside a certain space. The number of elements in a basis is the dimension of the space. So all possible bases for a vector space contain the same number of vectors, but the bases need not be unique, right? And a helpful fact that you may use in more than one occasions is that if you have n linearly independent vectors, those vectors form a basis for an n-dimensional space. So questions so far? Yes?
Could you explain the example of the one that wasn't closed under the
So, yeah. Let me write over here. Can everyone see if I write here? Okay. So let's say that I have two pairs, x1, y1, and x2, y2, that both belong in V. This means that y1 equals 2x1 plus 2, y2 is equal to 2x2 plus 2. So if I add those together, right, to get the addition vector, y1 plus y2 is equal to 2x1 plus x2 plus 4, right? So basically, this vector, let's call it V, and set this to y, is equal to 2x plus 4. So it is not in the initial vector space over here, right? Can you see? Like if I define, I don't have enough space. Define V equals V1 plus V2. So x comma y equals x1 plus x2. Right? Does everyone follow this procedure and see why the addition, why this space is not closed under addition? Yes? No? If I don't have the constant, what will happen? So I will still be in the vector space, right? I will still have the property y equals 2x. Does this make sense? Also, you don't need to show that everything does not hold. Guys, you don't need to show that all of the properties do not hold. You just need to show that one of the properties does not hold. The easiest property was that 0 is not contained. So I'm done. I don't need to check anything else. If I'm trying to prove that it is indeed a subspace, I need to show that all of them hold. Okay? Question?
If we had a three-dimensional, two linearly independent three-dimensional vectors, can we say that that's a basis for R2?
That's a basis for a two-dimensional space. R2 is defined as the space with z equals 0 formally. Does that make sense? Yeah. Yes?
So is basis a set of vectors or is it like a span?
Basis, very good question. What is basis? A set of vectors or a span? Basis is a set of vectors, the span of which creates a space. Right? So a basis is defined as a basis of a certain space. The span of those vectors creates the space. Question?
There were two slides for the criteria that formed like a vector space.
Yes?
So this one only like 4 things, and the one.
This is a subspace.
Oh, this one is like.
Yes. So this is space, this is subspace. Other questions? Yeah.
So for the slide that has a property of the vector space, could you give an example of when the associative property isn't told when was that done?
Well, in some weird cases where you may have nonlinearities, or depending on how you define stuff, right? The commutative property does not hold for matrix-matrix multiplication, for example, right? So if I grab like a set of matrices. Make sense? So I'll move on if there are no more questions. Yes, just one last question so that we stay on time over there. If it's a subset of Rn, how do you prove it? So basically, we will tell you what properties that vector space has. You remember there was a discussion question actually that we did that, right? And we said that the space is comprised of a certain vector that has element in the real numbers, right? So when the elements are in the real numbers, then by definition it is every element will be in Rn or R3 or R2 or whatever. Okay, I'll move on. So column spaces and null spaces. Now we introduced this concept of spaces, guys, in order to use them in this linear algebra formulation that we have, right? So we will apply them in matrices. And in matrices, spaces are very interesting when we consider the columns of a matrix. Each column forms a vector, and each of these vectors, if we grab them all together, their span is a column space. And also we will see what we call a null space, and it's very interesting. So if we have A1 through AN columns in a matrix of dimension n, the column space is the span of all of those columns. Now, this is also called, in jargon, a range of the matrix. The reason it is called range is that if you remember matrix vector multiplication, right? Whenever I multiply a matrix with a vector, I can write this as a linear combination of the columns of the matrix with the weights being the elements of the vector. So, essentially, the column space gives me all possible vectors that I can reach by multiplying this matrix A with any vector, right? So, this is also going to show us all y for which there exists an x such that A times x equals y, in other words. And as I said, the ideas of column space, span of all the columns, and range of A are identical. The dimension of this space is called rank of the matrix. But this is all jargon. The useful information is that the column space is just telling me which vectors I can create using this matrix. Right? Great. Now, the null space is a different set. It's the set of all vectors x such that when I multiply A with x, I get 0. So any vector x that is mapped to 0 using matrix A is in the null space of matrix A. Now, this is very related to the idea of linear independence that Annika presented earlier, and you have seen already, because if the columns of a matrix A are linearly independent, then the null space is going to be trivial. So it's going to have only one element, 0. Because always I can find one solution to AX equals 0, and that's x equals 0. Right? Now, if the columns are linearly dependent, then I'm guaranteed to have a null space that has dimension 1 or more. And we'll see what effect this has in a few slides. Now, the reason we're, as I mentioned, looking at column spaces and null spaces is that we want to see if a system of linear equations has a solution. Does it have a unique solution? Does it have infinite solutions or no solutions, right? So, essentially, as we said, if B is not in the column space of A, then there's no solution to AX equals B, because I cannot create B using A. Supposing that B is in that column space, then we know we are guaranteed to have at least one solution, and the null space tells us if that solution is unique or no. If the null space has 0 dimension or is trivial, then the solution is going to be unique, because all the columns are guaranteed to be linearly independent. On the other hand, if we have a subspace of dimension 1 or more for the null space, then we have infinite solutions to AX equals B. The reason for that is that, as we say here in the slides, any non-zero vector in null space of A, call it V null, right? If x equals u is some solution to AX equals B, and I add to this guy V null, if I distribute A, I get A times u plus A times B. A times u is B, A times B is 0. So I still get B, right? This is a second solution. This guy, u plus B now, is also a solution to this system. What if I get plus A times B now, plus random times of B now? Then I get essentially another solution, and another solution, and another solution, right? I have infinite solutions to this system when the null space is bigger than 1 dimension. Now, many of you may have been confused about how to find a null space, right? I don't even understand what a space is, how I show that something is a space, how do I actually go about finding it? All you need to do is essentially solve the system AX equals 0, right? So, what you need to do is look at the constraints and equations in the row-reduced form, and identify the free variables. As Annika showed earlier, the columns that do not have a pivot indicate which variables are going to be free, right? So you set those variables free, and then you solve for the rest of the variables with respect to the other variables. Then you have created essentially a vector where you have some free variables, some parameters. And this is essentially going to be a span of those vectors. So you factor out the parameters, and you grab the vectors with the numerical values that you have created. Please go ahead and see discussions for a example. The answers are online. The last example is a very thorough example on how to find null spaces, and it follows exactly this procedure. This is very useful. This is a very useful algorithm for finding null spaces in an exam. Okay? So, outlining the algorithm that I just mentioned, I want to find if my matrix is this guy, A, over here. I want to find all the solutions to AX equals 0, right? What I want to do is I want to row reduce. So by row reducing, essentially performing Gaussian elimination on this matrix, I end up with this matrix, right? What does this tell me about the null space? Right? I have linearly dependent rows. So essentially, I will have one free variable, right? I don't have a pivot in the z position. I set z free. I set z equals t with t in the set of real numbers. And then I go back and solve for y. So y plus 2z equals 0. Y equals minus 2z equals minus 2t. And same thing for x. X equals minus 4y minus 7z. It is equal to t. And then, what do I have? X, y, z. So t minus 2t and t. I factor out t, and I have this guy over here. The null space is the span of this guy. It is also a correct answer if you leave it like this and say that t is in R. These are two equivalent descriptions of the same thing. Is that clear to everyone? This algorithm that I've used to find null spaces? Yes.
So when we're finding null space, should we back substitute?
Yes, exactly. Yeah. No, as long as you have like the correct number of vectors, right? If you have linearly independent vectors, so if you have like 3 dimensions, you need 3 vectors. It doesn't matter if they're simplified, because bases are not unique. You need to have the correct number of those, and they have to be linearly independent. Yeah?
Just the first 2 columns.
Mm-hmm.
The first 2 columns, would that system be linearly dependent or independent?
If I did what to the first 2 columns, sorry?
So you Gaussian eliminated matrix.
Yes?
1, 0, 0, 4, 1, 0, 7, 2, 0. If you just had the first 2 columns, 1, 0, 0, 4, 1, 0.
So, this? So this is dependent, but you expect it because you have like cleared out the third variable and you only have 2 variables now. You have a 2-dimensional space, right? As we said, if you have more equations than unknowns, you're guaranteed to have linear dependence.
But if you take only the columns are linearly independent?
No, the columns are not linearly independent. Guys, can all of you see why the columns are not linearly independent? Why? I can right away find a combination. So 2 times this column minus this column gives me this column.
I mean, you're ignoring the third column and the left.
Yes, the left 2 columns would be linearly independent. Yes.
Even though you have that zeros.
Yeah, it doesn't matter. These 2 are linearly independent. These 2 are linearly independent. Any 2 are linearly independent. Yeah. Yes.
I think the question was related to an earlier question where if we have more equations than unknowns, then it would be dependent.
So, exactly, that's what we said. The rows are going to be dependent, right? The rows are going to be dependent. A useful fact that you will prove, please pay attention, guys. This is a very useful fact that you will prove in 16b. is that the number of linearly independent rows is equal to the number of linearly independent columns in any matrix. In any matrix. It could be a 2 by 3, a 2 by 10. So if I had a 2 by 3, right, I have 2 linearly independent columns, 2 linearly independent rows, right? If I get rid of this, how many linearly independent rows do I have? 1, 2, right? 1, 2 columns. This is a very useful fact that you'll prove in a later class. We're just giving it to you as a fact. Yes?
Is the rank of A 2?
Yes. The rank of A is 2. Because the dimension of the column space is 2. We have 2 linearly independent columns. Yes? Any other questions? The basis is the set of vectors that spans the space. So the basis would be written as... Thank you, yes. This is a bug in the slides. Thanks for pointing it out. Yeah. The basis is essentially just this vector, okay? The null space, this is what we say. Null space of A is the span. Yeah.
Can we write the column space as just those 2 rows, or once we row these, or should we write it as the first 2 rows?
Any 2 rows that you pick. So basically, the question was, how can we write the column space? You should pick the 2 columns that have a pivot. That's a recipe that's guaranteed to give you a correct answer. From the row reduced form. At least the upper triangular form. Okay, let's move on, guys. Let's focus. We have some material to cover yet. Great. So we did all this conversation about null spaces, column spaces, spans, dimensions, bases, in order to figure out a solution to the system AX equals B. It would be very simple if we could divide, right? But there's no such thing as matrix division. The only thing that's close to that is matrix inversion, which is only defined for square matrices. Okay? So when is a square matrix non-invertible? It's non-invertible, first of all, if it has linearly dependent rows or linearly dependent columns. It's also non-invertible when it has a non-trivial null space, right? If it has a 0 eigenvalue, which we will talk about later, or if it has a 0 determinant, which we will also talk about this later. Now, if any of these statements turns out to be false, the rest are guaranteed to also be false, so the matrix is going to be invertible. Okay? Now, let's talk about the determinant, since I mentioned it. The determinant is a very cool concept that essentially is giving us the surface, the area, formed by the parallelogram that these 2 vectors basically form. So if I have 2 vectors, this is AB, and this is CD. The determinant is giving me this area, as you have seen in class, right? So you only learn how to calculate determinants for 2 by 2 matrices. It is the cross products and the subtraction of the cross products, AD minus BC. And in 3 dimensions, they show the volume of a parallelepiped. Okay? Now, it's really important because when is a surface, when is this area 0, right? The area is 0 if and only if the vectors lie on top of each other. In other words, if they are linearly dependent. So if the matrix is non-invertible and it has a non-trivial null space. Guys, please keep it quiet so that the rest can pay attention. Is this clear to everyone? Any questions about the determinant? Yeah?
Will we have to know determinants for things like
No. So, with this, let's proceed to the concepts of eigenvalues and eigenvectors, which are really useful in order to describe dynamical systems, dynamical linear systems that evolve with time, right? So, this is the equation used to find eigenvalues and eigenvectors. I hope you guys have digested it so far. It's pretty big also. Trying to beat it into your heads. A times B is equal to a scalar lambda times B. So, an eigenvector is defined, of a matrix A, is defined as a non-zero vector, such that when I apply the matrix on that vector, it yields exactly the same vector scaled by some constant. That constant is the eigenvalue. We say that this eigenvector belongs to the eigenspace corresponding to that eigenvalue. Okay? So, the eigenspace that we've been talking about has infinite number of those vectors, eigenvectors, all of which correspond to a certain eigenvalue. Those things, it's really important to understand that they go in pairs. Okay? So, essentially, what I'm going to show now is how to find these pairs. A very systematic procedure that you're going to use for 2x2 systems to find these pairs. Now, notice that we wanted this equation over here to have non-zero solutions, right? This means that we wanted this equation to have non-zero solutions. What does this mean? We want the null space of A minus lambda I to be non-zero. And I just said that this happens when the determinant is 0. So I'm identifying all the values of lambda for which the determinant of alpha A minus lambda I is equal to 0. Right? This is a very simple equation. It will be some polynomial of second order, which you should be able to solve in order to get the two eigenvalues of this matrix. You could have multiple roots, so you could have like the same eigenvalue, just one eigenvalue with multiplicity 2. Right? Is that clear to everyone? For example, for a diagonal matrix. Now, after you have found the eigenvalue, what you do is you plug it back into the system and you solve for V. You're trying to find the eigenspace with this procedure, right? You're going to have linearly dependent columns and linearly dependent rows. So what you will get is an answer that has a free variable. So what you will get is essentially one line that is going to be an eigenspace. This is for 2x2 systems. Okay? Now, after you find this solution, any non-zero vector in that eigenspace is an eigenvector that corresponds to the eigenvalue lambda. These things go in pairs. Eigenvalue with a corresponding space, and any vector from that space is an eigenvector that corresponds to lambda, the specific lambda. Lambda 1 with space 1 and vector v1, lambda 2 with space 2 and vector v2. Okay? Now, some final notes. As I already said 3 times, 0 can never be an eigenvector by definition. Sorry about the typo. To find eigenvectors, you need to first find the eigenvalues. And then, finally, to this equation, as I mentioned, determinant of A minus lambda I equals 0 gives us all eigenvalues for which A minus lambda I times B has non-zero solutions, so non-trivial null spaces. To find the pairs, you plug them in one at a time, and you solve to find the null space. This will be the corresponding eigenspace. Okay? Just a recap of everything that I said. Now, before I go to PageRank, any questions? Yes. Let's keep it short, a couple of questions because we're running late.
So how would you like write out the eigenspace in like a mathematical format?
It's a span of a certain vector, right? So if you solve that system of equations, you will have a free variable. Is that right? When you factor out that free variable, you get a vector, right? The span of that vector is the eigenspace.
So then if we're not including the zero vector, how would we say that? Because the span can contain the
Yes. So the eigenspace contains the zero vector, but you cannot pick your variable. Your t has to be in r star now. It has to be non-zero. Okay? Yeah. Good question, though. Is that clear to everyone? Okay. I can feel everyone's getting drowsy, so speed up so that you can see problems. That's what you're interested in, right? Actual problems. Now, PageRank. That's a very useful algorithm, and we've seen it's a dynamical system. We want to see how people in the web hop from one web page to another web page, popularities of web pages. We've also seen this in the setting of water tanks hooked up with pumps, how the reservoirs change their levels at every time step. So we can use matrices and states in order to represent dynamical linear systems. Now, usually we do that using a transition state diagram, which is a directed graph with certain weights. The weights can show the percentage of water that leaks from one reservoir to another reservoir. They can show the percentage of people moving from one web page to another web page. But the concepts that we will use to analyze those systems are the same. Concepts of eigenvalues and eigenvectors. Now, look at this matrix, right? This diagram. And try to figure out the transition matrix T. The formal way to do this, and I really urge you to do this, because when even I or Professor Ranade or whoever tries to do it out right away, we all make mistakes. It's very easy. Double check where the arrows are pointing and derive the equations, right? So x of 1 at time step n plus 1 is going to be, how many times does it get anything from 2? Nothing. It only gets from 3 and 4. It's going to be x3 at the time step of n plus x4 at time plus 0.8. So let me write it out, sorry, so that everyone understands what I'm talking about, right? So x1 at n plus 1 is going to be equal to x3 at n plus 0.8 of x4 at n. If I write this out for all of the variables, I can then arrange them in a matrix, right? You've seen this multiple times in discussion and lecture. I keep doing the same procedure. So the columns essentially will tell me where stuff in node A will go, and the rows will tell me, so you see that from 1 to 1 I have 0, 1 to 2 I have 0.7, 1 to 3 I have 0.2, 1 to 4 I have 0.1. But formally do out the equations, please. And what the rows are showing me is what's entering a node, right? So what's entering 1? I just said 1 of x3 plus 0.8 of x4, right? Pick your way and construct the graph, the matrix. So let me ask you one question. Does the system look conservative to you? Yes, right? All of the columns sum up to 1. So no new stuff enters the system, no stuff leaves the system. Stuff can be water, it can be people that are surfing from web page to web page. It can be anything that we want to describe in this dynamical model. It can be the emotions of Romeo towards Juliet, and vice versa. So, as we said, if you have some greater than 1, stuff enters the system.
If you have some less than 1, stuff leaves the system leaks, and states will tend towards 0. So like they'll become neutral to each other, or they infinitely love or hate each other, right? Now, what we're interested in is if we apply this transformation multiple times, is this system ever going to reach a steady state, right? So if I apply to a certain state t, will the next step be the same as the previous one? And this will happen when? This will happen only when I have an eigenvalue of 1. But actually, if I wanted to calculate and I didn't have an eigenvalue of 1, I would go and say, hey, the next time step, I'll have whatever I have now times t. At n time steps from now, I will have whatever I have now times t to the n. This is more tricky to calculate, right? Now, if the inverse of this matrix exists, if I have linearly independent columns or rows, then I can go back in time. I can use the current time step to calculate one time step back. I can use the next time step to calculate this time step. Yeah?
If you t to the negative 2, can you go 2 time steps back?
Yeah. Now, so as I said, we're interested in figuring out what a steady state will look like, right? If my next time step is identical to the current time step. Now this looks pretty familiar, right? What does it look like? The eigenvector eigenvalue setting of a problem, right? Yeah, with lambda equals 1 at this time. Now, we want to find the vector that does not change when t operates on it. So, the not fun way would be to apply t n times. So, even applying it 4 or 5 times would probably take most of the people, including myself, more than 20 minutes. But the cool thing about this eigenvalue eigenvector theory is that we can use this linear algebra theory to calculate multiple time steps in advance if we have a steady state, right? So we want to find the eigenvector that has an eigenvalue of 1, and for this reason we're trying to figure out what's the null space of A minus 5, right? That's going to give us the eigenspace that corresponds to eigenvalue 1. Any vector in that space is a steady state. So no matter how many times I apply t to it, it will stay the same. So basically, here there is an eigenvalue of 1, and the corresponding eigenvector is this guy, right? But this guy doesn't give me any real intuition about the actual percentage of people that exist in in each web page, let's say, at a given time. The one last step that I want to do is normalize so that I can get the percentage. If all of these values add up to 1, right, then this means that I know from the first entry what percentage of the total amount of people on the web are in web page 1, what percentage is at web page 2, 3, and 4, right? In order to normalize, what I do is I basically divide everything. So normalizing is dividing x1 by x1 plus x2 plus x3 plus x4. This is my new x1. Right? And my new x2 is going to be the same thing, right? Dividing everything with all of these values. That is how I obtained this, and you can go ahead and check in your calculators. If you divide this value by the sum of all values, will it give this? So this means that at the first web page, there's going to be 35.8% of people, 25.08 in the second one, and so on and so forth. Now, the final part of this presentation is essentially derivations and proofs. Right? You've seen a lot of proofs so far. So, some strategies that I want you to employ using those proofs are start with what you know, right? Some people will give you some information, some given stuff. Write it out in math. And from that, start slowly involving the things that you care about, you want to solve. All right? Now, after that, based on the wording of the question, select a strategy to do this proof. Contradiction or constructive proof, for example. And if you're stuck, try a small example. Don't try the general example. Now, usually it makes sense if you just get a 2 with the proof to start over. But there's a really big post about tips on Piazza by Professor Ranade. I do encourage you to go ahead and check that out. And also practice until you become comfortable with these things. Yes?
When you said based on the wording, you can tell if it's constructive or...
Sometimes.
So what can we look for?
So, you remember that when we said that if A is non-invertible, then it does not have a unique solution. It's easy to assume that it has and reach a contradiction. That was the method that we did there, right? So, like, can it be raining without any clouds? Let's assume it can be raining without any clouds. Then when does the water come from? Okay. So basically, this is the last part of the lecture, and then we'll go to actual problems. So, you want to show, and you already showed that in lecture, that a 2x2 matrix with distinct eigenvalues lambda 1, lambda 2 has eigenvectors that form a basis for R2. What does this mean? That I have AV1 equals lambda V1, AV2 equals lambda V2, lambda 1 not equal lambda 2. This is in math exactly what the problem has given me, right? That's all the information the problem has given me. What I want to show is that V1 and V2 form a basis for R2. What does that imply? That they are linearly independent. If I show that, then I'm done. They do form a basis. Now, my strategy here is going to be contradiction. I'm going to assume that they are linearly dependent. That there is an alpha, non-zero, such that V1 equals alpha V2. Now, let's see what happens if I do that, right? Alpha AV1 can be written as A times alpha V2, because I assumed I can have that, right? Then I pull alpha out, and I have AV2 equals alpha lambda 2 V2, right? With me so far? Great. But V1 is also an eigenvector with eigenvalue lambda 1. So I can write that AV1 equals lambda 1 V1. But I assume that V1 is A alpha V2, right? So lambda 1 alpha V2. And I just reorder. But these are the same, right? So from these two equations, I must have that lambda 1 and lambda 2 are the same. What is this? This is a contradiction, right? It cannot happen to have like lambda 1 equals lambda 2. It contradicts our hypothesis, the given stuff. So, hence, V1 and V2 must be linearly independent. This means that they span R2 and they form a basis for that space. Okay? Now, a few general tips. I really feel that it's really important. Do you have any questions before I give you those tips? Everyone okay? Great. So, time management, I feel, is an important thing on exams. So if you guys get stuck, move on. Find a question that you're comfortable with. Build up some speed, warm up, and then you can always, if you have time, go back. Don't waste your time stuck on one question. Tackle as many problems as you can. As I said, also show your work. If you find a solution by inspection, just write out what you inspected and tell us that's the solution. And also, like for proofs and stuff like that, beware that you can only assume stuff that you were shown in class and homework. Note 6 has a lot of stuff that what we have actually proved and what is stuff that we have like told you. You can use stuff that we have proved. Okay? So that's it from me. Good luck to everyone. And pass it on to Perus to give you like a first problem.
Hello. Oh, can everyone hear me? I don't have that strong of a voice, so I'm going to be using the mic. Yeah, just look over the problem for a second. Okay. Everyone can hear me? I'm just going to hold this. Okay, so I'm going to start us off with a problem from a really, really old midterm about linear algebra. So just the basics. We're going to start off with that. Don't read into it right now. We're going to break this problem down to see how you can effectively extract out the important information to work with. But the general gist is Alice is a friend of ours who invested some money in the stock market through an investment firm, and she experienced the ups and downs of the stock market and how she reacted to that. So let's break down the first para. So she basically earned some money, and I'm just going to read the line. In fact, she is so rich that at the beginning of every day, she can put $1 of her money into the stock market. At the end of the day, she sells her stocks and looks at how much money she got. So the important thing we get from this is that every day she invests $1 into the stock market. So I always like writing this stuff down when you're writing your answer so that you don't get lost. Let's go to the second para. This is a lot of information. So it tells us that each company, we can record each company's growth on any particular day using the function GF, GS, and GD on any particular day I. So far so good? So we write that down. Then the next thing we see is a brief explanation about what this means. So it says, what this means is that if Alice invests $1 in friendly faces on day I, then she gets back GF $1 at the end of day I. So let's just write that down here as well, because we're going to be using it. Okay, now let's see how she actually invests in all of these companies. The problem says the mutual fund invests fractions alpha F, alpha S, and alpha D of Alice's money into each of these three companies. So let's write that down as well. Okay? And then it says, importantly, that these fractions are always constant. So far so good? Everyone's broken down the problem? Okay. So we have extracted all the information we need to work with. Now let's go to the first part of the actual problem. It says, using the terms defined above, write an expression using a dot product that would compute how many dollars Alice gets back after the first day. Okay, so let's see what happens on the first day. She's going to be investing her $1, right? And because it's a $1, when you multiply a 1 with a fraction, it's just a fraction again. So we know she's going to be putting alpha F dollars in company F, alpha S dollars in company S, and alpha D dollars in company D. All good? Similarly, for day 1, the functions that we had, G of F, G of S, G of D, can just be represented as G of F on day 1, G of S on day 1. So far, so good? And then, as we broke down, for any company, we just multiply the amount of money she put in with the growth function to get the amount of money she gets back. And because we invested in all three companies, we add up that total sum to get how much money she's going to get in return. Does everyone follow so far? Everyone understands how we got the last equation? I didn't get it my first time. I had to ask the head TA. You can ask me if you want. You sure? Okay. You're smarter than me. Okay, so we have that, but remember how the question told us to find a dot product that would help us compute this, because we are working with matrices. So let's break it down into two simple vectors. We have all the proportions, which represent how the investment takes place. That was alpha F, alpha S, and alpha D. So we can have a vector representing those. And then we had a vector, then we can have a vector G, which represents what the growth function for each company was on any particular day. So far, so good? So, as we can see, these two vectors can be combined in an inner dot product to get exactly the equation we started out with. Does that make sense? All good? Nice. And that's basically the solution to the first problem. Nice. This is going way smoother than I expected. You all are smart. Okay. Second part is a little bit longer. Okay, question. Yes. Yes, as long as you got the same equation, yeah, you can go either way with that. Okay, so the second part. Down here is just the carryovers from the first part that we observed, and let's break this part down again. So it says, let's assume on the first day, Alice got back $1.7. So remember the equation we wrote back there? That's exactly what that's equal to. Make sense? Okay. And then it says, on the second day, she again invested $1 at the beginning of the day. But this time, the stock market crashed. So she got back nothing. Kind of sad, but hey, that happens. So, for day 2, we calculate the equation in the exact same manner. But this time, the returned investment is 0. So, does everyone understand where we got these two equations from? Okay, question. Yes, that is a typo. Thank you. Everyone good? Okay. Let's go read the rest of the question. So, this makes Alice angry. Perfectly valid response as a human being. So she wants to find out what was the investment strategy that was being used by this firm she invested her money in. So she does some research and finds out that the growth functions of all 3 companies on the first day and the second day. So now we have the values for G of F, G of S, G of D on both the first and the second day. Okay? And now Alice wants to use this information to find out what the proportions being used were. So it was alpha F, alpha S, and alpha D. So let's use the information from the first part and just plug it in. So those equations, we plug in the values that were given, and we get those 2 equations. All good? Nice. Now, we need to realize that we have 3 unknowns in all the 3 alphas that we have to find out. But we only have 2 equations and 3 variables. So, this is a linearly dependent system, and we can't find a unique possible solution. But we need to. So, can someone think of one more equation? Okay. Yeah.
AF plus AS plus AD equals 1.
And why do you say that?
We were told at the beginning of the problem that the fraction sum of her money would also be $1, and that's
Nice. Did everyone hear him? Just to repeat. Yeah, because they're fractions, they sum up to 1, which gives us the third equation that we need. So now we have our 3 equations, and we go back to the question which says, write a matrix equation that Alice could solve. And now that we have our 3 equations, we simply translate that into matrix form, where the coefficients are on the big square matrix on the left. Then we have our variables that we multiply it with to get each single equation. Does this make sense? Nice. And we can use this equation by taking the inverse of the 3 by 3 matrix and multiplying it on both sides. Make sense? To get back. Okay, question back there? Can you speak a little up? Speak up. Yes, we're getting there. Oh, yeah. So we're going to find A inverse now, because we also wanted to touch on that in the review session a bit, but that's a perfectly valid way to do it as well. So I'm going to speed through this because it's math, and you guys can do it, because we also want to get the rest of the questions. But before we start finding the inverse of a matrix, we want to make sure it's invertible. And one way that was pointed out in this lecture was we can find the determinant and make sure it's not 0. How we can find the determinant is in a super easy and non-math intensive way is just play with the matrix a bit and convert it into the upper triangular form, and then you just multiply the main diagonal elements to get the determinant. As we can see for this one, it's 5. So we know that A inverse exists. The slides will be posted online, so don't worry about the math itself. But does that make sense? Okay, cool. So now that we know A inverse exists, we want to go forward and find A inverse, which is again some more math. Do I speed through this? Okay, so I can slow down a bit. So yeah, how do we find the inverse of a matrix A? We write down the augmented matrix, which is just the identity matrix next to it. And then every time we perform some sort of function on the rows of A, we just want to do that on the identity as well. So this is one thing I want to point out. Ones are the easiest to work with. So every time you see a 1, just swap out the rows so that it's on top and then work from that, because it just makes life easier. And in the exam environment, you do want to be doing as little math as you want. So we swap out row 1 and 3 to get the ones on the top. Then we use that to eliminate all the ones in the first column, everything in the first column. And then we essentially use the same logic for row 2 and 3, so we form the identity matrix on the left, and what we're left with on the right is essentially A inverse. And once we get that, we plug that back into our equation, and we get the values of alpha that we were after. I know I skimmed over the math, but it's only because we want to touch on the other problems properly. But yeah, question? Yes, but we just wanted to go over them. Yeah.
Another way to go about this problem would be just to do Gaussian elimination on the augmented matrix. And when you get all ones in the diagonal, you can just read off the answers from the last column of the augmented matrix. Is everyone familiar with this method?
Awesome. Also, we will be sending these slides out after, so if you do want to look through the algebra, you'll have the opportunity to do that and get some practice there as well. So now we're going to do a problem with relation to null space, which was on a past midterm. So why don't you take 2 minutes and just work on it individually and with the people next to you, and then we'll go over it together, okay? Also, if you have any questions during this time, you can raise your hand and we'll come around and answer it for you. For those of you, like now that the other two parts are hidden, the first one's asking what can you find the values for x for which M has a trivial null space. And the second one is say you have an x that makes it have a non-trivial null space and then find that null space. We'll give it 30 more seconds. Huh? That's it. It's really quick. No. Okay, who needs more time? Who wants more time? Who wants more time? Yes? Okay, we'll give it 20 more seconds. Okay. Can I get everyone's attention, please? Can you all hear me still? Yes. Okay, awesome. Just making sure. And let's get this back up. Yikes. Okay, so we have this matrix 1, 0, 4, 1, 2, 6, 0, 1, x. Anybody have an idea for how we can get started on this problem for finding an x? Yes. We can do Gaussian elimination. And what might our goal be? Well, let's see what that is. Let's start with Gaussian elimination. That's a great way to start. So let's do a row operation. Would it be okay if I subtracted row 2 by row 1? Is that okay? Okay, so I'm going to say row 2 is row 2 minus row 1. Okay, so row 1 remains the same. Row 2 becomes 1 minus 1, which is 0, 2 minus 0, which is 2, 6 minus 4, which is 2, and the final row remains the same. Okay, there's not much space here. From the center. Oh, no. Okay. Okay. Any ideas for the next step? What can we do? Shout it out. Sorry, could you say that again? Okay, sounds good. Would it be okay if we just first, or why don't, yeah, sure. Okay, so 1, 0, 4, we're saying row 3 is row 3 minus half times row 2. So we have 0, 2, 2, 0. What is 1 minus half of 2? 0. And what is x minus half of 2? X minus 1. Now, if this matrix has a trivial null space, which means it only contains the 0 vector, what must be true about x minus 1? It must be non-zero. And why must it be non-zero? Because if this was 0, then we would have a row of zeros, which means our rows are linearly dependent, and we have a non-trivial null space. But since we want it to be trivial, this means x minus 1 cannot be equal to 0. And that means, what does that mean about x? What must x not be equal to? 1. Okay. Does that make sense to everyone? Yes, any questions about that first part? No? Awesome. Okay. So, let's move on. Is it okay with everyone if I erase this? Yes? Okay. So we're saying that we will have a non-trivial null space if x is equal to 1. And so what the second part is asking is say, find what that null space is. So let's start by plugging in when x is equal to 1. So we have 1, 0, 4, 0, 2, 2, and before we had 0, 1, and we had x minus 1, and if x is 1, then x minus 1 is 0. So this is pretty much our matrix. And now we want to figure out what is the null space, right? So, sorry, this is a 0. Okay, so what does that do? When we have a null space, what is something we must choose? What must we have? One of the variables is a free variable. Awesome. So this is something you can choose generally. There's multiple options for what your free variable is, for which variable you choose to be that. Just generally, without fail, what you can do is choose the variable that does not have a pivot to be your free variable. So in this case, it's z. Okay, so let's say z is equal to some alpha, right, where alpha is in the reals. Can that be seen? Yeah? Okay, so if z is equal to alpha, what does the second row tell us? Remember, these are all equations, and we can think of this as augmented by zeros, right? Because we're trying to find the null space, which means this matrix times the vectors in the null space is equal to the 0 vector. So what does this tell us? What does, for example, the second row tell us? What is the equation told to us in the second row? Yes. Okay. Oh, yikes. I'm using x, y, and z here, so I can write that same thing as 2y plus 2z is equal to 0. That's absolutely correct. If this is the case, and we said z is equal to alpha, what does this mean about y? Y is equal to negative alpha. Okay, I'll write that out again. So we said y is equal to negative alpha. What does the first row tell us? How much times x? 1. How much times y? 0. And how much times z? 4. And that is equal to 0. If we said that z is alpha, what does this mean about x? Negative 4 alpha. Now we're trying to write this as a vector. We said x is negative 4 alpha. Y is negative alpha. And z is alpha. We can write this as a vector times our free variable alpha. That's negative 4, negative 1, 1. So what is our null space? Exactly, the span of negative 4, negative 1, 1. Okay, are there any questions about this question? Yes? So the way we're doing this is we're trying to set something to a free variable, right? And so we're saying z can be anything in the reals. And what is that thing that we've chosen it to be in the reals? It's alpha. Does that make sense? Okay.
Whatever is the set of real numbers. That's why I do this nomenclature. If we did it your way, our result would be the same times z, with z the real number. Doesn't make any difference. No.
All right. Okay, so the last problem we're going to do is related to eigenvalues and eigenvectors. It's an exam problem from last fall. So the problem basically says this. We're running short on time, so I'm just going to distill it into there's a flame war over pineapples between discussion TAs, and we're trying to capture the behavior of the students in a transition matrix as a result of this. So basically, each TA has an opinion on whether pineapples belong on pizza, and the students are going to be moving sections depending on whether or not they agree with that premise. We have this transition matrix M. This is given to us. And just so that there's no ambiguity about what exactly M is representing, like the convention we're using, we also have the exact matrix vector equation that we're using at the bottom. So it basically says that in order to get the number of students in each TA section for Elena, Nick, and Lydia, who were TAs 1 year ago, we multiplied the current values of those the number of students in each of those sections by the matrix M. So your goal is to fill in this diagram, which was very nicely provided on the exam, and each box is going to contain a value. And that value you're going to basically try and fill in each one from this matrix here. So, let's see. Who wants some time to do it? Who thinks, in general, that I should give you time to do the problem versus just going through the solution? It's a relatively long problem, so ideally we get through all of it because the last problem is a proof, and typically students like to see proofs. So who wants time to work on the problems by show of hands? Okay, nobody wants time to work on the problems. Does that mean, that means everyone wants to just see the solution as a walkthrough, right? Is that what we're saying? Okay, got it. So in that case, so we have this diagram, and we basically have to populate it based on this matrix here. Now, how can we interpret this matrix? It's basically telling us row and column. So Panos talked about this, which is basically that we can look at the rows as basically where are the contents of column 1 or node 1 or Elena going. And as a result, we can actually, it's hard to do this just skipping around, so I'll just go down here. Does everyone see how, actually there's no way you see that. Does everyone see how those equations at the top represent the matrix here? And we can just take the top row. So for example, the top row says 0.500. What does that mean? It means that for Elena, at the next time step, half of her students are going to come from however many students she had in the current time step. And she gets no other students from the other sections. That's what this matrix here is showing us. Similarly, based on that, can we see how 0.25, 0.5, and 1? What that means is Nick at the next time step is going to get a quarter of Elena's students. He's going to hold on to half of his students, and he's also going to get all of Lydia's students. And similarly for Lydia, she's going to get a quarter of Elena's and a half of Nick's. Now, when we create this system of equations, it becomes relatively simple translating it into words, how we can populate this diagram. So for example, let's just pick a random value. We have an arrow going between Nick and Lydia. That's going to be a fraction of 1/2. Why? Because we read it off from our system of equations and say, oh look, Nick, or rather Lydia at the next time step is going to get half of Nick's students at the previous time step. Does anybody have any questions about how we got to this state from this matrix here? Okay, all right.
So, the way you systematically write out this diagram is look at the first equation, right? The first equation refers to Elena. All the arrows that go into Elena can be found from the first equation. You're done with that. Then you go at the Nick node. What arrows go to the Nick node? 1/4 from Elena, 1/2 from Nick, and all of Lydia. I draw this out. And same way from using this.
It looks like there are just some empty slides. Okay, so what you're given now is that everything you did in part A was based on an incorrect matrix. So the things that Vladimir Stojanovic, who was the professor last year, he has this secret matrix, and the thing is that he wants to give it to you, but he's not sure whether your linear algebra is good enough. So his test for you is basically to find whether that should be the matrix V, to find whether this matrix has a steady state. So does anyone remember what it means for a matrix to have a steady state? What can we say about that matrix? Exactly. So our goal is going to be to say, okay, can we find the eigenvalues of this matrix, and can we show that one of them is 1? So the way we do that is we, of course, start with the given matrix, and initially this was going to to be a 3x3 example, but in the general case, I don't think you're expected to know how to take the determinant of a 3x3. So we simplified it to a 2x2. Yeah, like you all mentioned, lambda is 1 is a special eigenvalue, which basically indicates that our matrix would have a steady state. So first we form the matrix V minus lambda I, and when we do that, we get, instead of 0.4, 1, 0.8, 0.2, we leave two of the elements untouched. 1 and 0.8 stay the same. 0.4 becomes 0.4 minus lambda because we're multiplying lambda by the identity matrix and subtracting. And then similarly, 0.2 becomes 0.2 minus lambda. The characteristic equation currently has a bug in it. It should be 0.4 minus lambda times 0.2 minus lambda. That's going to represent A times D. And then you're going to subtract minus BC. So BC in this case would actually be 1 times 0.8. It's incorrectly written as just minus 1. But when you go through and you expand out the expression into the characteristic polynomial, you can find that you factor it as lambda 1 plus 3/5 and lambda 2 minus 6/5. So what that shows us is that we have eigenvalues negative 3/5 and 6/5. Are either of those equal to 1? No. So then we don't have a steady state. Yeah.
Just like a mental check,
Mhm.
can you look real quick and see that the columns add up to 1.2, which means that it's a non-conservative matrix, which means that it's either blowing up or zero.
So I'm not 100% sure you can make that assessment in the general case because it's possible if it has two eigenvalues, right? One of them is 1. The second one can be larger, and that would still have the possibility of things blowing up, but there is a steady state that exists.
Yeah.
I think that's right, yeah. So you only need one of your eigenvalues to be 1. So that would work as a sanity check if it asks, maybe for a different question, that kind of logic would make sense. Yeah.
So when they columns add up to 1, then you have a steady state, and then you can guarantee you have a steady state. When they don't, you cannot really steady state. It's like the example we did in discussion where we had 2, 1, and 1/2 eigenvalues. Then depending on whether or not you use the corresponding eigenvector, you blew up the system or not. Yeah.
Question?
We can take it after the review.
It's all columns add up to something greater than 1, though? Are you guaranteed one of the eigenvalues to be greater than 1? There has to be a way for it to increase somehow.
Yeah, I mean, intuitively I can say this, but I don't have a proof in mind, and I would advise against that type of deduction.
The things that the matrices we give you are typically going to be simple enough that you can just do the analysis. So for your own peace of mind, you may want to. For a much larger system, it may make sense to take that shortcut. If you can find a way to basically make sure that the logic holds, then yeah, go for it.
Also, can all people see how you factor this out from lambda square minus 3/5 lambda minus 18/25? Do you know of a way? The way to do this is that the two roots are going to be, if you multiply them, you will get the constant term, right? So lambda 1 times lambda 2 is minus 18/25, and the lambda 1 plus lambda 2 is minus 3/5.
And then if all else fails, just use the quadratic formula. If you can't remember it, put it on your cheat sheet.
Yeah, the quadratic formula is really useful because you will be asked time and time again to find the eigenvalues of a 2x2 system, so it's helpful to have this in mind. Yes.
Is it sufficient to show that 1 is not a root of that equation? Do you actually have to find the eigenvalues?
You can show that 1 is not a root. Yeah. Did you still have a question? Okay, perfect. So now Vlad is finally giving us the correct matrix. So this is our new matrix. We're calling it X. And now we are given that X has a steady state. And our goal now is to find a vector X that represents what that steady state is. So the approach that we take for this is effectively we need to find the vector X that satisfies the equation that is not here. Effectively, we need to find the null space of S minus I, because finding a vector that's going to be in that null space will allow us to solve for what that steady state is. So first we form S minus I, that's just going to be subtracting 1 from all the diagonal elements, and then going through and doing all the tedious work we can find what the reduced row echelon form of this matrix arbitrary variable here, which means that our null space is going to consist of a span of 0, 0, 1. If you answered during an exam, we basically clarified that it was going to be a non-zero vector. But if as your answer you put 0, 0, 1 or 0, 0, 2 or 0, 0, basically anything, that would be a correct solution. Because the span of 0, 0, 1 is pretty much any value alpha in the line position. Any questions? So we now have a new system which we can model with a different transition matrix. And without giving you the matrix, we're just giving you some eigenvalue, eigenvector pairs. So this kind of question is where intuition comes in very useful, because if you can basically look at the eigenvalues and eigenvectors and understand, like, oh, okay, if I have an element that's going to be aligned with V1, that is the 1, 0, 0 element, that's going to be part of the steady state. Whereas if I have something that's aligned with the 1, 1, 1 element, that's going to be part of the lambda equals 2 component. So this question was pretty much all intuition. There was very little calculation, pattern matching based on the 8 vectors that are given to you, trying to figure out which of those 8 vectors satisfy certain criteria. So the first question is, which of the vectors represent steady states of the system? Well, the steady state we said is something corresponding to lambda equals 1. That's something we've mentioned many, many times. And now we just have to find the vectors that are given to us of the 8, which ones are scaled versions of the eigenvector corresponding to the lambda value of 1. And we see that, for example, 5, 0, 0 is just 5 times that vector. And because they're aligned, that's also going to have an eigenvalue of 1, which means that that's going to be a steady state. Similarly, we look at 1026, 0, 0. That's also a scaled value, a scaled version of the same eigenvector. So the reasoning that they give here is very verbose and frankly can very much so be avoided during an exam with intuition. So this kind of approach will always work. If you're stuck and you're like, you know what, I know math, I'm just going to write it out, and even if it takes time, that's going to let me solve it, that will get you the correct approach, because you'll notice, for example, that C2 and C3 will be 0, where C1, C2, C3 are the scaling factors that you have for your different vectors, and that C1 is greater than 0. So ultimately, that will give you the same result as the intuition that I just described. But it is in your interest to basically try and develop intuition so that you can avoid the work. Similarly, we have a question of what kinds of initial states can we start with so that the number of students in the sections keeps growing? Well, we go back up here and we notice that growing means that a lambda value would be greater than 1, or rather the magnitude of the lambda value would be greater than 1. And so if we look at the last entry, lambda sub 3, that's equal to 2. So that would satisfy what we're looking for. And the eigenvector corresponding to that is 1, 1, 1. Let's look at the other 2 vectors. They don't have any kind of a component in the third position, because it's 1, 0, 0 and 0, 1, 0. What that basically means is if we have any kind of third component in our starting vector, that component is going to get scaled and scaled and scaled by a factor of 2 over and over until it blows up. And that is the intuition that we can use for this question, where we say, oh look, 0, 0, 1. That one has a component in the third element. That's going to grow. And we also have 1, 2, 3. That has a component in the third element. That's also going to grow. And that ends up being the solution, is those 2 vectors. Similarly, again, you can do the math or you can use the intuition. And finally, we have basically the last question now is what kind of initial states can we pick such that everyone ends up leaving the system? Well, if lambda is 1 is the steady state and magnitude of lambda is greater than 1 is growing, then the magnitude of lambda being less than 1 would indicate that we're losing people. We're hemorrhaging students actively as the semester goes on. So for that, we want to pick vectors which have a component as 0, 1, 0. And again, very similarly, if you go through the reasoning for that, we notice that the solution will be those which have scaled values in the second component, 0, 12, 0, and 0, 1020. So the last problem, which we'll see if we can finish it in 3 minutes, it's not a very long proof, but in terms of test-taking strategies, notice that this proof is worth 16 points. So, yeah, so the thing is that 16A and actually 16B exams as well tend to give quite a bit of weight to proofs in general, which means that if you can find a way to be concise and effective with proofs, that's going to net you a lot of points. And the reason for that is because proofs tend to be a distinguishing factor for students in terms of performance. A lot of students will see proofs and say, oh look, it's notation. Oh no, there are so many subscripts and things. I don't want to approach that. And that means they immediately get a 0 out of 16. Whereas if you can put together an argument for basically proving this, then that's going to get you 16 out of 16. At the bare minimum, it lets you have a little bit more breathing room in the simpler questions. Every single one of these was 6 points, and let's see. The transition matrix in the beginning was also 6 points. This entire problem was worth 52 points, and the midterm was 176 points. So just in terms of test taking strategies, it's worth noting how many points different things are worth. And that's also like, if you're stuck on a 6-point question, it's probably not worth your time. If you're in a position where you're looking at, say, a 16-point proof, and you think, I can spend a little bit more time and probably get it, that is much more worth it. So the idea here is basically that we have some transition matrix generalized to T, and the values, or our vector at the next time step is going to be given by multiplying this matrix T by the vector at our current time state. Now, we're given some information about T, which is it has n distinct eigenvalues and n associated eigenvectors with those eigenvalues. And naturally, the golden equation is that V equals lambda V. So our goal is to basically use the information we're given to prove that there is at least one initial state for which the system does not converge to a steady state. So intuitively, does anybody have any ideas? Maybe, maybe not. Yeah?
Insofar as lambda 1 is greater than 1, you know that something at some point is like causing it to blow up, right? So I feel like you could start constructing a proof from that and say that if like the variable associated to that is not 0, then it will blow up.
Right, so that's the intuition. Basically that if one of your lambda values is greater than 1, then you just need to find some value to scale that more and more and more as time steps go on. Did you have a similar idea? Okay. So this basically means, so we're just going to let V sub I be your eigenvector. So what actually happened for this was that the exam said V of 1 specifically, and then the solutions were graded, I think, for V sub I generally. So then the solutions were wrong, but then they backtracked. It's okay. Anyways, what happened is this is giving a more general solution, whereas we only really needed to worry about lambda 1. So notice that the exam problem is actually easier than what the solution is going to talk about more generally. We have this. So those 3 lines is basically, that's the entire proof. So if you got these 4 steps and could basically write out exactly what the person in the front row just said in terms of mathematical notation with reasoning for why you would go from each step from one to the next, then that would get you 16 points. Now, of course, proof doesn't mean that you can only use mathematical notation. You also want to supplement it with words if you want to explain something. But here's the general explanation. It's that t to the n, scaling our initial state, is going to give us what we get as time goes on. So if we can show that the limit of this is not going to be, is going to go basically to infinity as time goes on, for the case that lambda sub I, or in our case lambda sub 1 is equal to 0, then we've effectively completed our proof. So we start off with the form of the initial statement, which says that the limit as the number of time steps approaches infinity of t to the n times x of 0, where x of 0 is our initial state. Then we notice that we can also translate that to be equivalent to replacing the initial state with just the eigenvector corresponding to your first